Okay, good morning, and welcome to our panel on transformational improvement in data center power efficiency and sustainability. So, now I don't think I need to say a lot to convince this audience and the larger OCP community of the importance of this topic. I copied a few lines that came out in yesterday's keynote by IT Renew, I think Intel and Ampere. And like you can see, they're projecting, a lot of projections say we're going to be roughly 20% of the total electricity by 2030. I hope this community, by the way, does not let this happen, but we're at least at risk of that. We heard from Zane yesterday, we expect something like of the order of 5 billion cores. I think managing these cores for power efficiency is going to be quite tricky. But also, if you look at best-in-class PUE today, there have been many papers published, especially by Google. It sits around 1.1, but industry average is at 1.67. So there's almost 1/3 of that total energy that is yet to be, if you like, saved. We're also a very long way from compute energy proportionality. And I will have more to say about that, maybe in the closing remarks. The other thing also that is critically important, equally, is the peak power. Because most of the hardware is actually designed for peak power, not necessarily average power. And it's definitely a top limiter to both performance and driver of new hardware and hardware cost. Now, with this introduction, let me introduce my panel. Let me start actually with myself. I'm a power and performance engineer. I recently joined AMD, and I'm working on GPU power and performance. Prior to that, I worked for Microsoft for about 2 years on data center power efficiency. And before that, at Intel Corporation, again, power performance engineer for client devices and mobile. Now, my colleague, ex-boss and competitor, Zane Ball, he is Corporate Vice President in Intel Data Center, a platform group, and General Manager of the Data Platform Engineering and Architecture Group. He owns end-to-end engineering for Intel Data Center business and is responsible for inventing the future of data center architecture, design, validation, and deployment at scale. And then Marcus Fontoura is a technical fellow and corporate vice president at Microsoft, where he works as the chief architect for Azure Compute, and he leads the Azure efficiency team. Marcus worked on several projects, including container allocator, power management, liquid immersion cooling, and Resource Central, a machine learning infrastructure for resource management. And Professor Joshua Guess, he has spent nearly 20 years in the academic and industrial sectors researching novel cooling and thermal management techniques. His passion for innovation is matched only by his passion for education and his students. The student group he founded, OSU Overclocking, is the first competitive computer overclocking team in the United States. And last but not least, Dr. Peter Dubuc. Unfortunately, Peter could not be with us here due to strict government rules around travel. Peter Dubuc is a program director at ARPA-E, where he focuses on advanced cooling for electric systems and hybrid electric aviation. Prior to ARPA, Dr. Dubuc was principal engineer in thermosciences at General Electric Global Research. So welcome the panel, and I think we can start. Each of the panelists is going to talk a little bit about their company's action and vision for data efficiency, for power efficiency and sustainability. And we start with Zane. Oh, thanks.
All right.
Okay.
Good morning, Tawfik. Thanks for having us.
Good
morning. At Intel, and I talked a little bit in my keynote yesterday about our focus on sustainability at Intel, from everything from water savings to green power utilization, and driving energy efficiency across the whole operation. And I'm really excited to be here at OCP talking about sustainability, because I think the bigger opportunities are going to be at the intersections between the different industry players and how we work together to solve the bigger picture problem. Whether that's circularity and eliminating e-waste, or finding better ways to reduce carbon dioxide emissions, or just driving the efficiency of data centers overall. And that can be, I think at a chip level, and advancing Moore's Law, more advanced process technologies, but I think it's also got a tremendous architectural aspect, especially at the warehouse scale, and how we move workloads around and how we build compute architectures that are going to be more efficient overall. And so I'm excited about all those topics.
All right. And maybe next, Marcus, want to talk about Microsoft sustainability actions?
Yeah, I'm very excited to be here. Efficiency and sustainability are very key focus for Microsoft and for what we are doing in Azure. And we are trying to take a comprehensive view across data center, hardware, software, so that we can do a global optimization of thinking about the systems view of how can we design the workloads, how can we manage Azure, and how can we design hardware and data centers in a combined way so that we can minimize stranded resources, maximize efficiency, and design the software to take advantages of the innovation that we are doing in data center and hardware. So my team is focusing across the board in all these areas, and including understanding of workloads so that we can do better placement of workloads to minimize carbon footprint of workloads, liquid immersion cooling to try to minimize the actual physical resources spent on the physical infrastructure of the data center, hardware optimizations, but the key innovation for us is how all these things come together, and we can take an approach of using the software as a catalyst to make Azure the most efficient cloud and the most sustainable cloud in the world. So that's our focus, and then working also with developers and our customers, so that when they come to Azure and then they come to Microsoft, they have the sense that their workloads will be run in an efficient and sustainable way. And we are trying to take the burden as much as we can, both from internal teams for our first-party services that we have running in Microsoft Azure, as well as the third-party companies that host their services in Azure. So I'm
Thank
very
you,
excited.
Thank you, Marcus. And next, Joshua is going to talk about Oregon State. And
very cool. Okay, that works. Thank you, Tawfik. I appreciate it. I'm a professor at Oregon State University down in Corvallis, Oregon. And really, I guess maybe I'm a little bit of the wild card up here. But we're really trying to focus on building up the talent that the community is going to need moving forward to be able to address some of these real large global energy problems. And really, I'll kind of tell a story. The genesis of this wasn't necessarily I got into being a professor because this is what I wanted to do, feed y'all this talent. It was a student came into my office and he said, Dr. Guest, I love this stuff, but I didn't even know heat transfer was a thing. This was a senior coming into my office telling me he didn't know heat transfer and thermal management was a thing. Now, I could say, from my thermal fluid sciences, being a curmudgeon old professor, to say, well, that's his fault for not knowing that. But when you sort of take a look at how we've set up our education system at the college level, we have made it to where they don't get access to anything in the practical application space that would drive them, that would motivate them, that would give them that passion early on to pursue all of the different avenues of mechanical engineering, particularly heat transfer. So as a stuffy thermal person, it bugged me that the robot and the rocket and the car got these kids early on in the game, and by the time they got to me, they were like, well, shoot, I didn't even know y'all did this sort of stuff. So we developed a program, OSU overclocking, and you can see a lot of the pictures up there. And we've developed heat sink design competitions. Actually, Dr. DeBach was instrumental in getting that program off the ground as well. But we've really tried to engage students at the competition level, on a team building level. And what we found is that students who, actually I would prefer that they be freshmen and sophomores. Why? Because they don't know what they don't know. And so they go in and they'll burn stuff up and break stuff and learn that way about how to design and how to push the limits of these systems that we're trying to build, CPUs, whatever. And it's been really sort of inspirational to me to watch these kids challenge themselves amongst themselves. There's intra competitions that we have, but we compete online in international overclocking competitions through HWBot, and the students are really motivated to beat each other in those rankings and on those scale, or at that competition. So, again, I think that's just what we're trying to do is from the beginning, engage with the student, show them that thermal people and electronics packaging people in general are doing cool things, pun intended, but we've seen success with it. Our student group is over 80 kids. Now, about 20 to 25 of them are actively overclocking and competing, but I mean, we've got 80 students who are willing to tell other people that they're interested in electronics packaging. That's like a big step. So we're really excited about the growth we've seen.
Right, thank you, Joshua. And next, I think, Peter, I'm gonna put your slides, Peter, if you would like to go over it. Hi.
Yeah, sure. First of all, good morning, OCP, and thank you, Tawfik, and I'm very glad to be here. It's always good also to present after my friend Josh. I'm very glad to be here. I'm a program director at the Advanced Research Project Agency within the US Department of Energy, ARPA-E. You might wonder, why is ARPA-E at OCP? I think the earlier notes from the summary from Tawfik already said it. The energy of this sector is becoming quite significant. And it's my job as an ARPA-E program director to identify opportunities to explore and fund transformational technologies so that we can reduce its energy to the maximum extent possible. Now, this is an important space. Data centers are becoming a security, a secure framework for the infrastructure that many of us use every day, and a very important part of our US infrastructure. So anything we can do to make it more secure by reducing the energy usage is very important. And computing has really, I see that the energy goes through 4 flavors. You first go in as power, and there's been a lot of programs on power delivery and how to make that more efficient. I think there's been a lot of progress made there. The second part is the semiconductor that interacts with the software. So there's a lot of stuff going on over there that is very complicated. There's a lot of different roadmaps there. There's a lot of stuff very proprietary. And the fourth one is cooling. And cooling is actually maybe a little bit simpler to define because every watt going into a data center kind of comes out as heat. Sometimes I call them big hair dryers, not the 100 megawatt level perhaps. So I listened to many of the meetings today. I learned a lot about immersion cooling and the progress that's made, but my job is to really find what is the moonshot, the holy grail for compute systems is to look towards 2025 and 2030. And if we can pull up the slide now, that's really where my job is to see what are the nuggets of technology that we need that I can put in the toolboxes and then have students like the one Josh trains every day develop the transformations that are needed so that in 2025, the industry has the toolbox filled with technologies to make at least the cooling part of data centers to a minimal point of energy, as well as as a person, I'd like to actually also reduce the water usage, preferably to 0%. Now, I know energy sustainability is a focus for all of you. So you might wonder, how does that, an ARPA-E program, how would that, a potential ARPA-E program, how would that interfere with me or not? And I want to assure you it does not. We're really looking at what are the things that are so fundamental and so high risk, if they were to develop right now and be ready by 2025 or maybe slightly sooner, we can have that impact going forward so that we have a roadmap towards 2030 with the most energy efficient space. Now my holy grail of cooling, I kind of started with a blank sheet, what I my dream would be location independence, up to, let's say, very high rack power density, ultra low energy use for cooling, maybe modular, so that the mechanical plant becomes the footprint of a single rack. Of course, you need to be as reliable and simple to operate as air cooling. And I want to align the economic and energy optimums. We do see the immersion cooling work, which has incredible energy potential, but we still see what's being developed today, being rolled out as, there's a significant percentage that's not immersion cooled. So how do we align those optimums so that the best data center you could build is also the most economic as well as the most energy optimized? That's a discussion we'd like to have with this community. As you can see on this slide, we're launching a workshop on this topic, and we'd like to invite relevant parties to engage with RPE and have this discussion so that we together can define what I call the end zone, like in a football field. What's the end zone that we need to define that has interesting metrics so that we, as we explore what the community could do for that, see whether we can develop something transformational. Thank you.
Okay, thank you, Peter. Okay, very good. So next, we're going to start the Q&A. I'm going to start it actually with some warm-up questions, and then we're going to open it up to the audience. And my first question is for you, Zane. Basically, striking the balance between, let the fleet live longer, if you like, or renew, with a more power efficient, hardware. What's the balance from your point of view, from both, if you like, sustainability and financial point of view?
Yeah, that's a good question, and I think there's kind of two parts to it. It's kind of how do you make that judgment as a data center developer, and then how, as technologists, do we push the technology so we get better optimization points going forward. So I think you could just take a relatively simple approach and say, let's optimize for carbon emissions. And if you have good accounting and good metrics for everything are important baseline, something OCP could be a good place to work out. If you have good accounting, then you know what the carbon content of the hardware is that you're looking to upgrade. You know what the improved energy efficiency of more modern technologies is going to be, and you could simply make a judgment of, I'm going to upgrade, when the balance moves. So that's like a policy kind of thing for Marcus to decide. But then what can we do to help Marcus have a better answer? And there's a lot of things that we can do. For example, I was talking about modularity yesterday, right? So let's say we have a reusable, compute block, and now Marcus, in order to upgrade to the newest memory and CPU technology, is going, through a much cheaper and simpler process to upgrade, a standard module instead of upgrading a whole rack. So now the trade-off is now going to look really different. Maybe you upgrade much faster because you're not going to have that carbon deficit to pay off because you're just basically putting a circuit board there. And then I think beyond that, I think no one really wants to throw away infrastructure, especially if it can continue to generate profits. But maybe in orchestration and workload management, there's some clever strategies in sort of decomposing the task, and let's get the right infrastructure doing the right task to maximize the efficiency of the whole operation. Right? So I think we can get quite sophisticated, and then maybe but the most basic thing is we got to understand the scoring. I don't think we can underestimate the innovation that any company or any set of engineers can come up with. There's going to be really clever people, and if the goals are super clear, and then we can really work together effectively. If the goals are sort of vague and it's kind of hand wavy, then people are optimizing for their slogan versus optimizing for like that real result. So I think getting to that accounting, and then we can drive those technologies that make those trade-offs more profitable and more energy efficient at the same time.
Right, very good. Thank you, Zane. And my next question goes to Marcus. So Marcus, what's the optimal partnership across customer, developer, and the cloud platform in driving sustainability?
Yeah, so this is a good question, and I'll tie back to what Zane just said, right? So for instance, like if you look at one of the areas that's important for us is this notion of carbon-aware decommissioning. We have a system that has some formula that will compute the trade-offs. So like when should we decommission hardware? And then that can get arbitrarily complex the more we increase our understanding about the workloads, about our demand forecast, about like information that we might get from the data center build-out plans and grid information and so on, right? So our ability to getting telemetry from the hardware and understanding of the workloads combined will drive that decision, and that decision might vary depending on like geographic location and constraints that are like beyond like just like having a new processor that we can deploy or not. So this is one area, for instance, that is crucial for us, and then collaboration with the hardware companies like Intel and others, right, like crucial. So this is just one example, but like we want the platform to be smarter and smarter in automating most of these decisions. So for instance, in terms of power management, it's the same. Like over the years, we are trying to see if how can we use every watt that we have available in every data center that around the world. And definitely our most sustainable data centers are the ones that we didn't build, because we want to have data centers running at 100% utilization, and not only in power, but CPU and all across the board in all the resources, maximizing cooling, CPU and all that. So the trade-off for me is that I want the platform to do the most that we can do, but there is a limit of how much I understand the workloads. Like I will use machine learning, but like most of the workloads are black box for me. I can predict a few parameters, how much CPU they need, how much memory they need, will they grow their deployment or not, what are the deployment patterns, and what is their daily traffic. And but if the customers provide more data on their aspirations to be more green, like we can take that into account as well, right? But again, it will be a combination of like workload informed parameters, and then parameters that we use in the platform to globally optimize the deployment, right? I don't want to, like, let's say, if all my customers told me like, oh, deploy me in Sweden because like I have a green energy there, and then like my Texas data center becomes very empty, I'm wasting resources, and like in the long run, this is not the most sustainable thing that I can do across the board. So like this is again a combination between developers and the platform. And then the final point is that I feel in terms of like the programmers and the application developers, we want to evolve the platform to expose constructs like that they can express the desires for sustainability or like for efficiency in a more natural way. And then if I draw a parallel, for instance, with the mobile application development, like that they have constructs like suspend an application so that they can recover some battery. I also want to provide like these types of constructs for applications developers that are developing to the cloud, like things like they can say that the workload is regional agnostic, so I could move their workload around, or that I have like some time agnostic workload that like I can, this application is just doing a batch computation that I can defer it. So this gives me a huge amount of flexibility in placing it in the most efficient and most sustainable way possible. So again, it will be like a combination of like what developers can do in providing the constructs that you provide to them, what the platform can optimize for, and then what customers want. And I think hopefully we'll get to a good spot, like optimizing in these three constraints.
Thanks, Marcus. So my next question goes to Joshua, and the question is, with novel coolants and hardware on the horizon, what is academia doing differently to prepare students for the landscape?
Yeah, so OSU overclocking goes a long way in that. We really challenge our students to push the limits of the systems that they're trying to build. And so, they're cooling with liquid nitrogen, supercritical carbon dioxide, the dielectric coolants that have been talked about for immersion cooling here at the conference so far. And so there's that. So in that regard, it definitely does come down to the training of the students. But the one other piece of it that's not spoken about as much that I do think is critical is engaging with industry. And I'm going to say something that's kind of sacrilegious for a professor to say, but it's not about money. Asking y'all for money. It's really asking y'all for problems. So like, what problems are y'all interested in students who are coming in day one? What kinds of things should they be able to solve or look at and not freak out, right? So I would say earlier there was a image of a BGA and interposers and heat spreaders and all this. And then to the side, there was a little thermal resistance network. You would be surprised with how much it blows a student's mind that they can take something that looks so complex, a circuit board, whatever, and make that into a thermal resistance network and solve it or provide a boxed answer based on the equations and the knowledge that they have in their undergraduate textbook. It truly is a moment of success that you get to witness that's frankly kind of awesome. Example of that is, I run this electronics thermal management lab course. We passed around a PlayStation Vita. They took a screwdriver, broke it open, and I said, in 40 minutes, I want a junction to air thermal resistance network. And the students were passing it around, building up their resistance network, making assumptions on what materials it were, or what each material was, and they got it. So it's really trying to prepare them to be impactful on day one for y'all, because they need to be prepared for that. They need to be ready for that, to be able to tackle the issues that are going to come with novel coolants, novel thermal management systems, right? As I like to joke with my overclockers, if you can cool a Lambo, you can cool a Pinto, right? So if they can go in there and cool their sweet overclock system that's going to 600 watts, whatever, then, and I'm not trying to marginalize what y'all do with what I'm getting ready to say, but they should be able to go over and build a thermal resistance network for an iPhone, okay? And that's kind of what we're trying to drive on that front.
Very good. Thank you, Joshua. And my last question is for Peter. So Peter, I'm personally involved in few volunteer activities at OCP, but the one thing I notice is the lack generally of engagement with DOE, and maybe in particular ARPA. So my question to you is, how can we engage with ARPA on this topic?
Thank you, Tawfik, and actually I love also how the other panelists mentioned topics that will line up with that quite nicely. So the first one is just email me. You saw my email on the screen. You can also reach out to Tawfik or others, and my email address is quite out there. Zane mentioned something very important earlier. He said, can we define the goal? What is the goal that would really make a difference? And that's, I think, what ARPA-E's role could be in potentially in working with OCP and the entire community that works on data centers. And I really call it something bigger, compute efficiency, because it's beyond data centers. I want to include edge. I want to include co-location. I want to include 5G, AI, machine learning. There's a lot of compute in the entire country. If we can define a goal or a target that is a moonshot, and those minds of people that Zane mentioned, if you put engineers and give them a challenging goal, they will achieve it. They put people on the moon 50 years ago. We can make the cooling challenges for this industry go away as long as we can define a challenge and fund it. ARPA-E funds transformative technology paths, but we need to define that goal together. It's also something that Josh mentioned. If I can, in the workshop that we plan to have, we are going to try to work as a team to see what would be a goal that would be very challenging. Now, I could say, let's put a 200 kilowatt per rack in Miami on the worst day that we can imagine, and then make sure it has to be dry cooled with the PUE of 1.01, or I could even, with maybe a supply line running at 75 Celsius. So that would be a pretty hard goal, but I need the refinement of what are the right metrics to frame a goal that's both hard, yet still also transformative if it were to be developed. Now, these are all potential potential programs. If we can define it, I can bring that to DOE leadership, and we can explore whether that could be a challenge. And student teams like Josh could then team up with industry and others to explore such goals. Because if we can engage all the minds that we have in this field, students, academia, industry, we can achieve anything we want. And that's what I truly believe. But we have to define the goals properly, engage with RPE, join us at the workshop, email me directly, and we'll have conversations and see how can our agency help potentially this area. That's what we'd like to explore. And the first step is reaching out.
Very good. Thank you, Peter. And I'd like to take some questions from the audience now. Kari?
Thank you. I have a question for Intel. We've done some life cycle assessments on servers, and we really see that where carbon intensity is the highest is within the chips. So whether it's CPU, memory, and SSDs, and anything that requires wafer production. So I'm curious to know more about what Intel is doing to reduce the carbon emissions associated with that manufacturing process of the chips that you guys are making.
All right. I think our biggest focus is in trying to improve the power source, because it is a complex industrial activity to manufacture wafers. And so while we can improve the energy efficiency of our operations, and we've made big investments in doing so, and we'll be able to improve it, but I think it's still going to be a relatively large energy cost in order to do that level of manufacturing. And so we have to continue to transition our operations to green power sources.
Okay. Yeah.
Hi, this is Vaidehi from Microsoft, and I have a question for Intel as well. So in your presentation yesterday and even today, you were talking about reducing e-waste. Intel is looking forward to reduce e-waste, and you also talked a little bit about having circular centers, etc. So my question is, like, what are the different strategies that Intel is employing to reduce e-waste at various levels? And also, when it comes to the circular centers, is it component level sabotaging or recycling of components, or are you looking at like larger scale, server scale, like going forward 5 years from now, right now?
Well, I think through like the OCP circularity work group, it's where we want to get to understanding how we bring the entire rack level, circular system. There's a lot of things you can do, and I'm not an expert on it, but there's a lot of things you can do at chip level materials recycling. There's a lot of valuable materials in that. I think that's a relatively mature industry, but there's probably still a lot more that we can do. Intel plays a big role in defining, at least for our platforms, how our platforms are designed, the kinds of chassis that they go in, for high-speed signaling, the kind of material sets that are going in motherboards. And I don't know that we're always doing that with the level of understanding of what the full cycle looks like. And I think one of the reasons we're leaning in on the OCP work stream is we need to learn better about what those end states look like. So as we architect future standards and future platform designs, that we're pushing towards the right material sets and supply chains to achieve, I think, as I said yesterday, I think it needs to be, less than 1%. I mean, we need to just think virtually everything must be in that circular supply chain. And I don't think we have a clear enough idea yet exactly what actions we need to take across all those different materials.
Thank you.
Okay. We'll take the next question.
Steve Harrington, Shieldine. This is kind of a question for Microsoft and Intel. We've been hearing from other Microsoft people about overclocking, and I know with Intel generally your server chips are limited in the speed that they run, depending on how much you pay for them. So is there a way that we could set up a system where Intel gets paid, for speed, and that when renewable energy is plentiful, you speed up the chips, get more work done, and when renewable energy is not plentiful, you slow them down and save energy?
So do you want me to answer? Or is it?
Yeah, you guys can.
I love to pay more, Zane.
I like that.
No. So like for me, I think like we are trying to understand the workloads and see when we need to speed up things, right? So like for instance, like there is a lot of data that for instance, like after the lockdowns, we saw that like there is a spike every hour, like 2 o'clock, 3 o'clock, 4 o'clock on the Teams usage. So at that point, if we are in a capacity constrained region, can we use extra cycles through overclocking to avoid like delays for that service at that time, right? So, and we want to selectively use overclocking like for applications that need it, or if you have extra power that we need to use, and we can scale more, install more compute there. So it will be another mechanism that for us that will be available in the data center. We have like how to effectively use it when appropriate, and I think like we have like so far like very good collaboration, not only with Intel but with all the other vendors, like explaining the scenarios for us, and then this will be an active area of collaboration for many years, I think.
Maybe if I can add to that, we do see a challenge with there's excess renewables in some area of the country at some parts of the day, and I think if data centers were to be much more modular, like they would be the size of a single rack or maybe half a rack, maybe even houses could have their own micro data center, and a software solution would distribute loads around the country. So that if California has a lot of sun, New York sends their through the fiber their loads over to California. So those kind of vision would be, we've discussed, that requires both solution and hardware innovations. But it could be very interesting. If somebody takes a shower, you should never run an electric heater. You should always run a computer, and the computer would power your water. So if you go in a swimming pool or anything where you need heat, can you use? But that requires a different way of thinking about computing, as well as some software solutions that would allow it to distribute. And currently, if you look at data centers, it's the processor, the server, the rack are very modular. It's the mechanical plant that's not, and the power conversion part. And if we can, one of the visions is if you could make all of that much more modular, so it could be scaled to different scales, maybe some more of those solutions could proliferate. But that's a little bit of future think.
And I was going to make a comment. Today, the chip is actually very flexible in this regard. So the core will dynamically change its power, voltage, and frequency as necessary. A lot of our customers don't want to do that, though, because they value what they call quality of service, right? They want to have a virtual machine. They want it to perform at a very predictable pace. But if you have the software ability to steer things in a dynamic way, the chip is very capable of ratcheting up performance and voltage and power, or bringing it down very low. And then there's a whole architecture of power saving states, right, where you can achieve very low levels of power depending on the latency at which you want the chip to respond. So those kind of technologies exist today, and we also have a capability we call speed select technology that lets a customer pin particular cores at particular points on that curve in a predictable fashion. And like sometimes like a network provider might take a network function virtualization workload and allocate certain cores to that workload, and then we can dial in the performance and power consumption to an optimal level. And so when Marcus wants to order up his solution, we can customize all of those configurations for a customer, and in fact, a great deal of it's customizable even without Intel's direct involvement. If you were someone that we were working with every day. But you touched on something else though that I thought was interesting. Set aside just the technical answer to that, which is, should we be thinking about the chip as a service versus just as kind of a device, right? And I'm often interested in that question. Like how can I work better with Marcus? It's like just thinking of it like I'm providing compute as a service to Azure's platforms, and can I do that in a way that's better indexed against their real business need? And I think there is something to that. The aircraft industry, went through that transition, and the engine manufacturers sell power by the hour, right? And they're constantly working with their airline customers, right, on how to improve efficiency and fuel consumption of the fleet, not just in selling the engine as a one-time sale. So I think there is a future for us in thinking about how we align the incentives in the supply chain towards those goals. And I think they will be dynamic. They'll have to do with how data centers are architected. And I think, as Marcus pointed out, how workloads actually are internalized, right? And today there is this kind of opaqueness in many cases to what the workload is really doing. Intel doesn't have a lot of visibility into that. And if you're in the IaaS kind of environment, and you know, Azure doesn't have visibility into that either. And so if we could find the right way to communicate the details of the workload, you know, even if it wasn't dynamically, and just have the indexes of what was needed somehow pass through this stack without endangering the security of anyone's data or intellectual property, you know, then we could probably act on it and make something better.
Right, because right now your pricing is, I'm going to buy this, you know, Xeon chip that's at 2 megahertz and it costs $5,000 bucks, but if I buy a 3 megahertz one, it costs, you know, more, and it has turbo mode, and go do that for a little while, but it comes back down to its normal speed. But I understand as your process gets better and better, you know, your binning chips at 3 gigahertz could easily run at 4 gigahertz, you know, so the question is, could a customer say, oh, you know, I want the special code to type into my chip and it speeds up, you know, and that way you could...
Yeah, those things are possible. Those things are possible.
Okay, thanks a lot.
Yeah, we have a paper, I think, on ISCA last year, and then Yannis is just sitting across, so you can talk to him about like what our vision for overclocking. But like I do agree with you that to be a very dynamic and low latency operation, like all the features that we want from the hardware, like not only overclocking, but like for power management, voltage domains, and so on.
Right, because I'm also coming from a liquid cooling direct to the chip perspective, and obviously if it's at night, we can cool the chips much better than we can during the daytime if we're running on cooling towers. Maybe you guys can take advantage of that.
Okay. Yeah. Thank you, folks. We'll take one more question, maybe from the audience.
Thanks for bringing this great topic here. OCP is certainly a great place for you know, abstracting various levels of solving this problem, top-down, up, hardware, software, all of that. And Zane, I just could not stop thinking after your talk yesterday and research today about you know, 5 billion in 4 years and 20% in 9. With that, setting a good goal is what you set some targets. That's good, but also comes to mind the thinking that you know, with the geographical democratization of database or data center installations across the globe and various regulatories involved, is this enough to? Is the industry? Of course, we can come up with all sorts of engineering solutions, but is this good enough goal? Do we need some kind of regulatory push? How do we go across globe? You know, making sure, because various use cases, like Marcus is saying, can have various solutions, and you know, so it gets very, very complex. That's what I'm trying to get at. How do we make sure that actually does happen globally, not just you know, one company or you know, one silicon or one type of compute or whatever you may have.
Yeah, I think it is challenging. It's not unique to data centers. It's not unique to the tech industry. I think we do have a global problem of addressing carbon emissions of you know, industrialized economies, and you know, in a world where you have many national programs, different tax regimes, you know, and different technology bases. You know, it's not entirely clear, you know, how you create all the right incentives to go push various industries to go, you know, reduce emissions fast enough to achieve those goals. And I think if we, among this industry, which does have a particular global nature, you know, if we adopt goals of, you know, getting 10x kind of improvements, number of companies have made, you know, big commitments, and then we follow through with those with the supply chain, you know, we can make, I think, significant differences, and put the right incentives in place for the kind of innovations that'll make a difference.
Maybe if I can add to that, so our agency doesn't do policy. We explore other technology paths that lead to greater efficiency that also buys its way on commercially. So I think regulations, to some extent, can be very helpful. They also can constrain a problem in a challenging way. So if you can, the first ideal path would always be if you can find technology paths that are more more both technically achievable as well as economically the most preferred. And right now, if you look at, for instance, chips, they are hotter than ambient. Second law of thermodynamics says we should be able to push heat from A to B. But there are many historical ways in how the current data center infrastructure has grown. And so are there technical paths that could be explored to make it better? That's something our agency can at least push to the furthest as possible. And if these technologies get developed in the US through US scientists or others, that could potentially be an export product. So that's why it's for our agency interesting to see can we support not only this sector by all the semiconductor support that's been given, but can we also explore the hardware side of the problem, such that we have a vibrant community developing the best technologies. And I think there's still some room for growth, and I'd like to explore that together.
Very good. So I think the clock is saying I have a little bit less than a minute, so I'll try to close very, very quickly. I know we're between you and lunch. So for closing remarks, I'd like to put a challenge for the next 5 years, or so. And I think you've seen Zane's keynote, and I think he challenged this community, hey, what about 10x reduction in CO2 and less than 1% e-waste for data center bomb? I think we should take that very, very seriously at heart. I think these are very good challenges. But also, like they say, the best, most cleanest energy is the energy that doesn't get used at all. Yeah. So in addition to that, I'd like to put some challenges on things like average power reduction. And I would say, maybe for the next 5 years, hopefully when we'll have another panel with the same audience, we'll see that we have achieved that. And I'm proposing 50%. This is not entirely arbitrary, really. There is some science behind it, basically on average power reduction. Primarily by improving compute energy proportionality. There's a very good paper by Google in year 2007, actually, and a very good comparison, I think by Luis Andre Barrasso, very good comparison between the mobile devices and what they have done and the data center. And of course, the data center is a lot more complicated because you have multiple clients on your processor, and whatever one client is doing, sometimes the blast radius is, quite big and affect what other clients are doing. So it's a little bit more complicated. But if you look at the devices, particularly mobile, it took them about 20 years, but they achieved order of magnitudes, actually power reduction in average power. Things like in the past, you plug in USB in a laptop. USB itself consumes few milliwatts, but it causes everybody to be high alert and consumes watts, basically. There are kind of things going on in the data center world. Again, a little bit more complicated because of the multi-client, but I think that 50% reduction should be achievable. The other one is, I think, peak power, right? Because a lot of the performance is driven by the peak power, and the hardware is built for peak power. Your device may be consuming, on the average, 10 watts, but there are instances where it's consuming 100 watts. And you're going to build the hardware, the power delivery, the power distribution system, for that 100 watts, actually. So you can imagine how much e-waste you're doing, basically, for those very little instances. And the challenge is to eliminate that completely, basically, and just build your hardware for average power with better power management, better utilization, and storing and shifting energy. So with that, I'd like to conclude, and thank you very much for all your questions, interest, and hope to see you next year.
Thanks, Tawfik.